Right, this is going to be our first unit, our first video for the light unit. We can see our learning goals here describing what light waves are, what polarization is, color pigments, rules for color mixing, and explaining our sky's different colors. Light is the only thing we can see. And it's probably the sense that we rely on the most. We know that during the day, the primary source of light is our sun. Secondary sources would be like the brightness of the sky. Other common sources would be like flames, filaments in light bulbs, glowing plasma in your TV screens, all that stuff. But in all cases, we find that light originates from the acceleration or the accelerated motion of electrons. And this is important because when we have charges, electrons are charges, when we accelerate them, they have an electric field surrounding them, and then when they move, they get a magnetic field around them. So by moving them, there's both a magnetic field and an electric field. And so by having the acceleration motion of electrons, light is produced. Light is an electromagnetic phenomenon, and it is only a tiny part of a larger whole wide range of electromagnetic waves, which we call the electromagnetic spectrum. Sometimes I call it the EM spectrum. So if you were to take a stick and shake it back and forth in some water, you'll produce waves on that water surface. Just like, and if you were to shake a charged rod in empty space, you'll produce electromagnetic waves in space. So again, remember that moving charges create a magnetic field around them. Moving charges lead to a changing magnetic field, which, and according to Faraday's law, leads to a changing electric field. So the vibrating electric and magnetic fields regenerate each other and make up this electromagnetic wave. It emanates from the vibrating source, so these accelerating electrons, and the strength of the induced field varies depending upon the speed of the particles here. So what we have here, get a highlighter. So what we have here is we got this changing electric field, and it produces a changing magnetic field. And notice that the magnetic field and the electric field are always perpendicular to each other. And where the magnetic field is 0, the electric field is 0, and where the electric field is 0, the magnetic field is 0, where they're the strongest, they're strongest at each other. But these two fields vibrate together, and this produces our electromagnetic wave. So if we're looking at a vacuum, all electromagnetic waves move at the same speed, which we call c. There's many myths about why we use the letter c for the speed of light. I'm not sure which myth is correct, but we use that. And that's at right around 300 million meters per second, so 3 times 10 to the 8th. The waves differ from one another in their frequency. So this classification of electromagnetic wave by frequency is what we call the electromagnetic spectrum. We have detected electromagnetic waves with a frequency as low as 0.01 hertz and on up. So with this, we have our spectrum. Now this section right here, this is what we see in. This is the part of the spectrum that is visible to our eyes. This is the part where our rods and cones allow us to actually see it. Any frequency lower than that, we have infrared, microwave, and radio. We cannot see those. The frequency, the wavelength is too big for our eye. And likewise, ultraviolet, X-ray, and gamma, the wavelength is too short for our eyes to detect. So really what we're capable of seeing is a very, very small part of this entire spectrum. So EM waves with frequencies of several thousand hertz are classified as radio waves. when you turn into your radio, you may notice like 99.3 megahertz. So that'd be an example of a radio wave. Very high frequencies, television is about 50 million hertz. Still higher frequencies are called microwaves. We use those in microwave ovens. Then on up. Infrared is often called heat waves. We can feel those. Then we get visible light. Makes up less than 1/millionth of 1% of the EM spectrum. The lowest frequency of light we can see appears red. So that's why infrared, infra meaning below, so infrared is the waves that are below red. Violet is the highest. Ultraviolet will be above violet. Higher frequencies, ultraviolet, higher energy. High frequency means high energy in these waves. These cause sunburns, potentially skin cancer. Higher frequencies, extended X-ray, which can go right through you, gamma rays. There's no sharp boundary between these regions. Okay, that's something that's kind of important. There's no sharp boundary between these regions. They kind of overlap a little bit. But we still break the spectrum up into those arbitrary regions just for classification's sake. We can use a little bit of math. Remember that the speed of a wave equals its frequency times its wavelength, so we just swap out the V for a C. Same math that we did for other waves. Now for polarization. Light itself is a transverse wave. So that means its wave motion is perpendicular to the particle motion, which for particles, really it's the field vibrating for these. And what that means is the direction of the electric field is perpendicular to the direction that the wave is moving, like shaking a rope. The waves on the rope would be perpendicular to the direction of the rope. So electromagnetic waves, like rope, are polarized. If you shake them up and down, the relative motion, we say it's vertically polarized. If you shake it side to side, then it's horizontally polarized. So here's how we can kind of generalize this EM wave. It's either vertically polarized or horizontally polarized. If we take a look at light from a light bulb or the sun, it consists of many waves, and a lot of them have different orientations. Some are vertical, some are horizontal, some are any and all angle in between. We call that light unpolarized. So that's light from the sun, light from a light bulb. It's random, it's everything. But we can make it polar by passing it through a filter. And then this filter, you can't see it, but there's trillions, or maybe not trillions, but millions of lines, and they're all vertical. Okay? So only the vertical light can pass through. Or maybe it's a different polarizer that's horizontal. So only the horizontal light can make it through. But by having the light pass through this filter, we now call it polarized light. So here I've got something that's unpolar going through a vertical polarizer. It's like a fence post or like a fence, and only the vertical parts of that light can get through. The rest of it's blocked. Now there are several ways to polarize light. For example, when light bounces off of glass, water, or asphalt, some sort of non-metal, it tends to become horizontally polarized. Okay? Now this has a special name. We call this glare. So when you're driving and you experience glare, what you're really doing is you're having sunlight reflected off the road and into your eyes. We call that glare. And again, it's generally horizontally polarized. So what we do is we wear polarized sunglasses. And what they do is they only allow vertical light to pass through. So it removes glare. We call that anti-glare. So since water typically reflects light and becoming, horizontally polarized, fishermen love polarized sunglasses. It reduces that glare and makes it easier for them to see the fish under the water. Okay, so this was actually one of your CLAs earlier. Some people got it, some people were kind of hit or miss on it, but this is really what's going on. Sunlight becomes horizontally polarized when it bounces off of water, so we block that horizontal light, and it in fact acts like sunglasses. 3D movies kind of work the same way. So when you look at an object, you have two eyes, you're seeing the same object from two different angles. Your brain uses this information and it uses it to judge distance. So 3D movies kind of take advantage of this to trick your brain into thinking the images have depth. So you wear special glasses, and the most common are these are polarized. You got two polarized filters with different orientations. So really what you're watching is you're watching two movies at the same time. One movie's for one eye, the other movie's for the second eye. And your brain puts these two images together to give you a sense of depth, which I think is really kind of cool. They used to do this with filters, like a red filter and a blue filter, but I think the polarized ones just make it a little bit crisper, a little better image. All right, I think the last thing I want to discuss with you is color, for this video anyways. So even though light vibrates very fast, our eye can still distinguish different frequencies. And for sound, frequency went with pitch. For light, frequency goes with color. There are 7 colors that we can recognize. We've got this acronym Roy G. Biv: red, orange, yellow, green, blue, indigo, violet. And we can see this when you pass a light through a prism. So what we can do is we can take a look at the math. So using our V equals frequency times wavelength, we can substitute the V for C, 3 times 10 to the 8th. So frequency is speed of light divided by wavelength. So for each color, we can go through and we can calculate the frequency. So I think that's another assignment, another CLA assignment I had for you. So here you can see the different frequencies. A little bit of trivia here. Newton was the one who kind of coined some of these colors here. He passed light through a prism and saw this rainbowing effect. And you may be wondering, what color is indigo? It seems kind of a strange color. He made it up. Newton wanted 7 colors to match the 7 musical notes on the Western scale. So there you have it. And also, violet's not purple. Violet is actually a blue. Roses are red, violets are blue. So just some trivia kind of stuff right there. White light is a mixture of all these colors. So when all of these colors enter your eye at the same time, your brain can't handle it, and it just interprets it as white. So the white light is not a single frequency, it's a mixture. So a rainbow is created when sunlight, which is white light, passes through raindrops. Raindrops act as a prism, and they kind of bend the light at different angles. We call that refraction. And the amount that a wave refracts depends on its frequency. So when the sunlight enters the rain droplet, the water is refracted. Each color is refracted or bent at a different angle, separating the white light into its different frequencies. So that gives us the different colors here. And you can kind of get an idea from this picture which frequencies bend the most. So it looks like longer wavelengths like red, lower frequencies, bend more than shorter violet or bluer wavelengths. All right, so I think that's going to be a good place to finish up this video. I'll see you in the next video.